I'm Jim Heffron. These are my lessons in Calculus 1, and what we're working on now is the homework for the material on infinite limits. Okay, let's have a whack. So let's see. Here we go. Here's the document camera. There we are. All right, so let's see. The first problem I always make a thing of. The first problem is going to be taken from a prior section because the way that we keep things fresh in our mind is by keep pulling them back up again out of our memory. So I'm going to pull back up out of my memory the definition of limits, section 2.2, and it happens to be question number 7. Let's see if I can find the darn thing. Here we go. Question number 7. And I should give credit to the book since I'm showing it. This is the Stewart Calculus book. So it says, for the function g, whose graph is shown, find a number a that satisfies the given description. Of course, here's the graph here. So the first description is limit as x goes to a of g of x does not exist, but g of a is defined. So the limit doesn't exist, but g of a is defined. So I've got to find a number a that satisfies that description. Here the limit doesn't exist, but g of a is not defined. Here the limit does not exist, and g of a is indeed defined. That's what the closed circle means. Here the limit does exist, g of a is not defined. So 4, a equals 4 is the only correct answer here. Part B, we've got to find the number a that satisfies a given description. Limit as x goes to a of g of x exists, but g of a is not defined. So we talked about those. So let's see, limit exists, g of a not defined. That's going to be a equals 5. Can you see the little circle on the camera? That's going to be a equals 5. C, limit as x goes to a from below of g of x and the limit as x goes to a from above of g of x both exist, but the limit as a whole does not exist. So there's a limit here for x equals 2. There's a limit from below and a limit from above. They both exist, but the limit as a whole does not exist. So that's correct. 4 is also correct. There's a limit as x approaches 4 from below. It looks like it's about a half to me. There's a limit as x approaches 4 from above. That limit looks like it's about 2.2 to me. But the limit as a whole does not exist. Here the limit as a whole does exist for x equals 5. And then finally, limit as x goes to a from above of g of x equals g of a, but the limit as x goes to a from below of g of x is not equal to g of a, and that's x equals 4. Okay, so that was the first one. I went back to a prior section because if you keep going back and going back, that's how you get it really in there. So let's see, now I'm moving on to section 2.6, and the first problem that I want to have a whack at is I want to look at example 4. I picked that example because the book does something slightly different than I do. Let's see. Example 4. So it says, find the horizontal asymptotes of the graph of the function f, and it's the square root of 2x squared plus 1, there we go, square root of 2x squared plus 1 over 3x minus 5, and we're looking for horizontal asymptotes. So I'm going to take the limit as x goes to positive infinity and the limit as x goes to negative infinity and see if I get a limit for either of those two cases, or maybe the limit is the same in both cases, and that'll be, either one would be a horizontal asymptote. I'm going to copy that to my paper because I want to talk about what's done here in just a second. So the limit as x goes to infinity and x goes to minus infinity, we're looking here at f of x equals square root of 2x squared plus 1 over 3x minus 5. Okay, and we're going to take the limit as x goes to infinity. And we know that for large x's, when you look at a polynomial, you only have to pay attention to the term with the highest power. So inside that radical, I'm only going to be paying attention both for plus infinity, x is approaching plus infinity, and x approaching minus infinity. I'm only going to be paying attention to the 2x squared. And on the denominator here, I'm only going to be paying attention to the 3x. So when I take the limit as x approaches plus infinity of f of x, I'm looking at the limit as x approaches plus infinity of the square root of 2x squared, and on the bottom is 3x. So what I get is the limit as x approaches plus infinity of square root of 2 times x. Of course, x is positive, so when you take the square root of x squared, you get x. And on the bottom, I just have 3x The x's cancel, and I'm looking at a total limit here of square root of 2 over 3. So that's going to be a horizontal asymptote is y equals square root of 2 over 3. Okay? Now let's look at what happens when x approaches minus infinity. The limit as x approaches minus infinity of f of x, and of course much of it's the same. The limit as x approaches minus infinity of the square root of 2x squared over 3x, and that's the limit as x approaches minus infinity of, again, I'm taking the square root of 2x squared, so you get the square root of 2, and when you take the square root of x squared when x is negative number, then you've got negative x and 3x. So I end up with minus square root of 2 over 3. The x's cancel, and I end up with minus square root of 2 over 3. So there are two different horizontal asymptotes, plus square root of 2 over 3 and negative square root of 2 over 3. Now in the book, he gives perfectly reasonable, but different than what I did. He justifies, when I talk about paying attention only to the leading term, he justifies that through this algebraic manipulation. He takes square root of 2x squared plus 1 over 3x minus 5, and he sort of divides top and bottom by x, and x is going to infinity, so you don't have to worry about x equals 0. Divides top and bottom by x, then he algebraically rewrites that, and he ends up with a calculation that gives him the same square root of 2 over 3. So he's justifying the result here that I just simply cited as you only have to pay attention to the term with the largest power, because he's saying limit as x goes to infinity of 1 over x squared is 0. And likewise in the other case, he does basically the same thing. Okay, so the example that he's got justifies the fact that I simply cited, that you only have to pay attention to the largest power in when you take a limit of a polynomial where x goes to infinity. Okay, great. So let's see here. What's next is I'm looking at the homeworks, and I'm looking at number 3, number 15, and number 23. So number 3, whoops, I got to flip back. Something under my book. There we go. There was something under my book. Number 3. Too much stuff on the desk. So number 3 says, for the function whose graph is given, state the following, and then we're looking at things like limit as x goes to infinity of f of x, limit as x goes to minus infinity of f of x. And of course, it's just a picture, so you're supposed to do the best you can with the picture. You're supposed to make out. Strictly speaking, over here, you could have funny things happen, but come on, you know. So limit as x goes to infinity of f of x. What happens when x gets very large? I think, I'm only guessing, but I think we're supposed to imagine that the function has leveled off and that the graph, and that you're looking at y equals minus 2. A person could say, well, I thought the graph continues to fall. That would not be a ridiculous thing to say. In any event, as long as you had some idea what was happening, we're simply looking at what's the y value when x gets bigger, bigger, bigger. Same thing for minus infinity. We're looking at what's the y value when x gets more and more negative. And I think the way the artist has drawn it, that we're supposed to take it to be 2, y equals 2. So I think we're supposed to have horizontal asymptotes of positive 2 and negative 2. But again, somebody who raised a hand and said, I really thought, it's not a ridiculous thing to think. This says the limit as x goes to 1 of f of x, and I think what you see is x is slightly below or x is slightly above 1. I think what you see is that the y values are coming to be more bigger and bigger positive numbers. So I think that we're supposed to take that to be positive infinity. Both on the left and on the right, they're bigger and bigger positive numbers. So we take that to be positive infinity. And the limit as x goes to 3 of f of x, I think we're supposed to take that to be negative infinity. Okay, so here we're looking at x equals 1 gives you a limit of positive infinity, and here we're looking at x equals 3 gives you a limit of negative infinity. So the asymptotes are x equals positive 1 and x equals 3, and the horizontal asymptotes are y equals minus 2, I think, from the picture, and y equals 2. Okay, so that was question number 3. Next up is question number 15. Gonna need a protein drink after this. So let's see. It says limit as x equals to infinity, 4x plus 3, 5x minus 1. It says find the limit or show that it does not exist. So 4x plus 3, 5x minus 1. X is getting larger and larger in the positive direction. Let's see. The limit as x goes to infinity of, what is it now? It's 4x plus 3 and 5x minus 1. So we pay attention only to the term with the highest power of x, and I get the limit as x goes to infinity of 4x over 5x. X is going to infinity, so I don't have to worry about x equals 0. So I just simply get 4 over 5. So that's the limit. It's just that simple. All right, let's see, that was 15, and then the last one I want to do is 23. Maybe I'll spare myself carrying the book over and just copy it to the page. So let's see, 25 is the limit as x goes to infinity of square root of 1 plus 4x to the 6th. Can you see that says 4x to the 6th power? And on the bottom of the fraction is 2 minus x cubed. Okay. So as x goes to positive infinity, paying attention only to the leading term in this polynomial, I'm looking at the limit as x goes to positive infinity of the square root of 4x to the 6th. And on the bottom is minus x cubed. So I take the square root, and I've got the limit as x goes to infinity of 2x to the 3rd over x to the 3rd with a minus sign in front of it. Carrying that down to the next line, I've got here the, I guess I'm going to write it, limit as x goes to infinity of 2 over minus 1. And so just simply looking at minus 2. Okay. Now, I talked about the example 4, where he justified all this, and I absolutely could have done the limit as x goes to infinity of the square root. So I could have done the limit as x goes to infinity of the square root of 1 plus 4x to the 6th over x cubed, all over 2 minus x cubed over x cubed. Maybe I need parentheses there. And it would have eventually led to the same minus 2. So not his process of working through with the, in this case, x cubes, is by no means crazy or dopey. That's just not true. But I'm skipping those steps and just simply saying you can just take the leading term in the polynomial when x goes to infinity. Okay, all right, very good. So ready for next time.